So yeah, please, Gianluca, go ahead.
Okay, I was getting ready. Sorry, didn't notice everybody had come back in the meantime. So hello, everyone. So on Monday, we left double field theory. And I think I managed to introduce you to the idea of trying to do something similar to double field theory, but for exceptional groups. And that's indeed what we'll do now. Let me remind you of something might help. Sorry, I'm still arranging my stuff here. So in double field theory, we had basically, what were we doing here? We had a metric, a B field, and well, also a dilaton, but for this review, I'll just forget about the dilaton. We embedded them into some object H called the generalized metric, HMN, which is parameterized by GMB, and indeed actually defines a coset space, which was also 10,10 over SO 1,9 square. So let's say belonging to it, meaning that it parameterizes the space. And then we said, well, we tried to define something called generalized diffeomorphisms based on doubled vectors sitting in the vector representation of SO 10,10, such that when they act on H, they reproduce infinitesimal diffeos and the gauge transformations of the B field. And we saw that, in fact, in order to write an object like this in a form which is O10,10 covariant, we had to, in fact, generalize our derivatives. Notice that I'm switching to M instead of mu for the space-time indices. That's what I'll do for ExFT in a second. But perhaps for now, let me go back to what we were doing last week, which was mu indices for non-doubled space-time. The idea was that in order to have something that looked O10,10 covariant, we had to embed the physical derivatives inside a doubled derivative. And then the theory itself, namely closure of generalized derivative, told us that there had to be a section constraint, which looked like this. We had the O10,10 metric. And this is really an algebraic constraint telling you that these D's, these del's here, really need to sit in an isotropic sub-vector space of the vector representation, and possibly a maximally isotropic one. And up to O10,10 rotations, the only choice is to pick the original 10 derivatives, but you might do rotations and then interpret these rotations as T-duality whenever you have, well, you can try to interpret them even when there is coordinate dependence for all 10 coordinates. But of course, usually in T-duality, you expect to have an isometry, and then you may parameterize, you may make a choice of coordinates such that the isometric direction corresponds to one of the coordinates, and then you lose one of the coordinate dependencies. So that's the idea anyway, okay? What I want you to focus on is the idea that you embedded fields into appropriate generalized objects, and you want to reproduce gauge symmetries in terms of a generalized derivative, okay? And the section constraint will show up somehow forcibly from the construction. So I want to do it for the exceptional case. So let me remind you what we had there. If we are to do a Kaluza-Klein reduction from 11 or type 2b, as we mentioned in the first lecture, we end up in some D equal 11 minus n dimensions. If you start from type 2b, I still count D as being 11 minus n, treat it as the definition of little n. Hidden symmetry is parameterized in some ENN space. And then we have fields, an external metric, a bunch of vector fields in the R1 representation. which is not necessarily a vector like O1010, but it's given in tables you find in the lecture notes. Scalar fields parametrizing a generalized metric, which I call M now, just because that's what usually happens in the literature, which, just like for H in the other case, it parameterizes a coset space, which is En divided by its maximal subgroup, compact subgroup. And then other p-forms like B mu nu with some, I don't know, some other indexing, some other representation R2 and blah, blah, blah. And you keep going, okay? So that's just from Kaluza-Klein truncation, okay? And when you do that, you do get to write an action for maximal supergravity in the dimensions. And this action will look, well, rather reasonable. There's going to be an Einstein-Hilbert term. Then there's going to be up to some factors, a term which contains the derivatives of the generalized metric. This looks just like what we discussed for type 2b in the case of SL2. The raised indices mean that's the inverse matrix. Then you will have kinetic terms for your vector fields, and then kinetic terms for all the other p-forms. And then possibly, depending on the dimension, sometimes you also get a topological term. Like in 5D supergravity, there is a Chern-Simons-like term, even in the ungauged maximal supergravity. There are more details depending on the dimension, like indeed what other p-forms show up. In even dimensions, there are some p-forms which are going to be self-dual. So there, for instance, in 4 dimensions, you have 56 vectors, but actually they are related to each other by electric-magnetic duality. Half of them are the magnetic duals of the other half. But yeah, let's not get into those details. I just want you to get the idea that at the end of the day, you have a theory, which is a gravitational theory coupled to a bunch of scalars, a bunch of vector fields and other p-forms. And the only other thing that probably matters is that the kinetic terms are non-minimal, the scalar dependency in the kinetic terms. And then you may have a topological term and other details depending on which dimension you have picked. So now that's a d-dimensional theory. Now I want to plug back all the Kaluza-Klein towers. I don't want to do a Kaluza-Klein reduction. I just assume I did the very same rearrangement of fields as one would have done to get here in Kaluza-Klein reduction. But I let all my fields depend, sure, on the d-dimensional external spacetime, but also on y coordinates. And I use capital Y because just like for double field theory, the idea is that I will, when we were discussing Kaluza-Klein, we were using a little yn. But for the same reason in double field theory, we had to double the number of coordinates to get something that looked like ODD covariant expression. Here we will need to extend the internal coordinates to a full R1 representation, capital Y with a capital N. Okay, and eventually we will meet a section constraint telling us, well, yeah, you did that, but you really need to restrict yourself to a smaller set of coordinates in the internal space. Okay, the other difference with double field theory is that in this case we are leaving some external spacetime unextended. Okay. The reason for that is that if we don't do this split into 2 pieces, then we have to do E11 exceptional field theory, and that's much harder. Definitely not good for a first course. Okay. So what we're going to do now is I'll just postulate how a generalized Lie derivative should look like, and then I'll tell you how you get to the expressions that show up in the literature. Clearly not going through all the details, but at least the general idea should be clear. So feel free to interrupt if you have any questions. Let me remind you something we did in the second lecture. The idea now is that we have some generalized vector in the R1 representation of En. And we want to define, these are generalized vectors. And I want to define a generalized Lie derivative with parameter lambda acting on another generalized vector. And that should be a transport term. And then there should be a rotation term, but it has to be projected onto the algebra of En. The reason for that is that we want eventually this thing to act on the generalized metric. The generalized metric satisfies some identities telling you that it's an element, it parameterizes the En over K of En coset space. To preserve those identities, you can only act on it via so-called rotation, which is itself an En element. Okay, so now I'm writing the generalized derivative acting on a vector instead of the generalized metric, but eventually you want it to act on a generalized metric too, right? So what you're gonna have here is some projector, and I'll give you a better definition for this in a moment, that projects, as the name suggests, the derivative of lambda onto En. And then in principle, there could be also some density term. Actually, there will be a density term. Okay, so that's the general structure you expect. The density term will be 0 for the generalized metric to preserve its determinant being equal to 1. But when I act on a vector, that's the structure. And the first thing I want to do is to understand how generalized diffeomorphisms work by themselves, ignoring how they will act on all the fields of the theory, because that, of course, will take longer. So,
Gianluca, can you hear me? Is there a
yes.
V? Is there a V contracted also in the second term?
Yeah, there is definitely one. Thank you. The minus sign is too large. Trick me. Vn. Let me write it in red. Vn. Okay. The only free index has to be n, just like on the left-hand side. Okay. So what is this projector? Well, let's say that my generators of the En algebra, I call them T alpha, where alpha is the adjoint index. And then I want to write them in the R1 representation. So I'll just use this expression, okay? I'll stick to the R1 representation. Then the projector P is nothing but some normalization, the Cartan-Killing metric for this algebra, which is simple or semi-simple depending on dimension, T alpha, NM, T beta, Q beta. Okay, order of indices is just a matter of preference. Okay, and of course this is a projector, meaning that P square is equal to P. Maybe let me write it once. QPRS is equal to P MN/RS. And this fixes the normalization. I'm not committing to it because it depends on whether you want the Cartan-Killing metric to be actually the Cartan-Killing metric or perhaps normalized in a different way. So you'll have to check if you look at the literature what the conventions are there. Okay, but so that's the general idea. That's actually quite restrictive, right? We only have two coefficients. For small dimensions, like for n small, you may have more, like in 8 dimensions, E3 is actually semi-simple, SL3 cross SL2. So actually the projector decomposes into 2 pieces. You have 2 coefficients alpha, blah, blah, blah. But the general idea is this one. This thing is actually quite restricted. But how do I fix them? Well, I could fix them by saying that, well, actually, I'll come back to that. First, let me rewrite this expression a different way that will allow me to explain better how you fix those coefficients. I'll write it like this. I'll keep the transport term. And then I will add what you would usually get if this were a standardly derivative. Right? If I stop here, this is just a standardly derivative in R1 dimensions for R1 dimensional vectors. But then there has to be something more. And this something more, whatever it is, I just call it Y. Okay? In double field theory, you would have this Y MPQN. It would have been just eta NP, eta QN. That might help you put things together. Okay? The only thing I know so far is that this Y object is a constant and it's invariant under EN and also under the trombone scaling we mentioned in the first lecture. You can deduce it from, you can compare these two expressions and deduce the expression for Y, and it will depend on alpha and beta. Okay, eventually I'll just give you the expressions for Y directly in the lecture notes for a couple examples. Perhaps it's better if I write it anyway. Just one time. YMPQN is going to be equal to delta MQ, delta PN, minus alpha, the projector, MNPQ, plus beta, delta MN, delta PQ. That's just the translation between the two expressions, nothing more, nothing deep here. But let me remind you of these two coefficients we still need to fix. Okay, so how do we do that? There are two ways. You could construct generalized diffeomorphism from first principles. After all, you want to say two things. You want to say that L lambda on the generalized metric gives me the gauge transformations you expect from the higher dimensional supergravity, like from 11D supergravity, where M is parameterized by the internal metric, the internal tree form, the internal pieces of the sixth form, if any. And then you construct this structure. Another way to do it is, but then if you do that, you somehow need to already know what the section constraint is supposed to be, no? Because we certainly need to restrict the number of internal derivatives. So what I'm going to do is something slightly different. I'll first point out something, and there's an exercise that asks you to check this. No matter alpha and beta, closure requires the following constraint. YMNPQ, whoops, dn equal to 0. So this is your section constraint, and this is just going to show up from requiring closure in a way similar to what we did in double field theory. However, depending, this is no matter, regardless of the values of alpha and beta. Depending on alpha and beta, more requirements could show up. So we'll fix alpha and beta to be those coefficients that allow me to drop any other requirements. Give me the minimal set of constraints. on the derivatives. I'll need a little bit of room to write that. So let me scroll out the first expression for the Lie derivative and keep the second one only. There exists a unique choice of alpha and beta for each dimension, such that, let me call this the section constraint. As C above is the only requirement for closure. Okay. And quite coincidentally, or perhaps not, that's exactly the right choice that will reproduce the resulting L lambda reproduces on section the gauge transformations of the Sugra fields. Of the Sugra fields inside the generalized metric. It is too abstract. Let me remind you, in double field theory, one of the things we mentioned was, well, now that we have this generalized derivative, act on H, perhaps even decompose H in terms of a coset representative V, act on V, on section, and see that you actually get exactly the transformations of G and B, corresponding to an internal infinitesimal change of coordinates and the gauge transformation of V. So you could do the same thing here for all the fields that look like scalars in D dimensions. So all those that enter curly M.
A quick question. Is there a deep reason why these two methods agree? A priori, can you say why?
I think that's non-trivial. Okay, so there are a few reasons. One intuition you can have is the following. One way to guess what this Y should be is to notice that actually the Y tensor projects the tensor product of two R1 representations onto the representation of the two forms. So why does that matter? For maximal supergravity, there is a constraint, there is a condition on half BPS objects to be mutually half BPS, meaning that you could superimpose two half BPS particle like solitons and say, well, the whole solution is still half BPS. That requirement is exactly that if the first half BPS object has charge Qm and the other has charge Pn, well, their projection onto the R2 representation, which is proportional to this Y tensor, needs to vanish. Okay. And the way you can interpret this is it's telling you that if you want to enhance your D-dimensional maximal supergravity with more degrees of freedom capturing some of these solitons, the ones you can pick are those that correspond to internal momentum. You cannot add more internal momentum and also some extra rings. Okay, that wouldn't give you local supergravity or even a meaningful theory in higher dimensions. So there is this kind of intuition that these two things need to work out because of this reason. It starts breaking down at 4 dimensions and lower, where there are a few more elements inside Y. Y is not just this projector, but that's the general intuition. Okay. I hope that answers the question.
Thank you. Yeah.
Okay. So I have 2 things to mention in a few minutes, because then I want to get to generalized Schwarz. If there are any other questions, this is actually a good time. Okay. So let me put a parenthesis here. I should also mention, yeah, this interpretation works well here in maximum supergravity. You could play the similar game here for other duality groups, like those of half maximum supergravity, or perhaps even on supersymmetric theories. then yeah, this specific interpretation doesn't work anymore. Yeah, I don't know what's the best interpretation of this fact in the other cases. So there are two important pieces of information to tell you now. One is, recall that we could reach a d-dimensional maximal supergravity, both from 11D supergravity or from type 2B supergravity. Type 2A is 11D on a circle, so I don't count it here. Okay, that's how you get an ungauged, undeformed d-dimensional maximal supergravity. As a result, the section constraint has two maximal orbits of solutions. Remember, in double field theory, we said however you solve the section constraint up to 10,10, it's always the same solution, assuming it's the maximal one if you lower the dimensionality. Here instead, you have two solutions. One is 11-dimensional supergravity, and one is type 2B. These are found by decomposing En into either its, well, perhaps let me say ENN cross R plus, just to be a little bit more precise. Into either its GLN subgroup. You remember there was such a subgroup from the Kaluza-Klein section. It has exactly the interpretation of the standard diffeomorphism along the internal space. Or under a GL n-1 times SL2. You do this branching. Let me make a little bit of room. You branch the R1 representation in those two cases. And in both cases, you get a fundamental charge +1 under either GLN or GLN-1 plus ... And if you select your derivatives, well, that's R1 prime, no? Because it's the derivative with a lower index. These are going to be your physical derivatives. And then the rest has to be 0. And that solves the section constraint. You make all your fields depend only on those coordinates associated with those internal derivatives. And your whole exceptional field theory boils down to 11D or type 2B supergravity. Obviously, this is not a proof. I'm just telling you, the proof will take way, way longer. So before I stop on this and ask you for questions, let me give you one example. And you find another two in the lecture notes. I have to scroll a little bit more, sorry about that. Do stop me if you need to. If you need me to. So the example I'll take is the first simple one, which is SL5, which means D equals 7 external spacetime. The R1 representation in this case is the 10, which is this representation of SL5, the doubly antisymmetric. So I may introduce indices in the fundamental 1.5, and then my lambdas will be written as 2 antisymmetrized indexes in the fundamental, and the same for the derivatives. Okay, I hope that's clear. And it turns out that the Y tensor, Y, A, B, C, D, E, F, G, H, all double index notation, is in fact nothing but a fully antisymmetric delta with a coefficient in front, which depends on your conventions for double index contractions. So I won't write it. And so the section constraint becomes del AB, del CD, all antisymmetrized, equal to 0. What are the solutions to this? Let's make even a little bit more room. Well, solution one is you pick dm5 different from 0 only, and you drop with m equal to 1 to 4. This breaks SL5 to, well, SL5 cross R plus to GL4 times R4, which you recognize, hopefully, times R0. Oh, well. Times another rescaling, which is the 11D trombone, plus R4. Though if you're confused about the R plus factors, ignore them, it's fine. You won't need more details. The other choice is you take now the index M to mean only 1, 2, 3. And then you only pick DMN, always antisymmetrized, different from 0. This breaks to GL3 times SL2, semi-direct product, a bunch of stuff. So this is 11D supergravity section, and is the type 2B supergravity section. Then you'll find that there is, as we discussed in the first lecture, no changes there. You can parameterize the generalized metric in terms of fields sitting exactly inside these groups. And then you have a natural action of generalized diffeomorphism on that parameterization of the generalized metric, just like you had a natural action of the generalized diffeos in DFT on the G and B parameterization of curly H. And then one can actually compare and see that you reproduce the correct set of gauge transformations. I'm not going to do that. Okay. And then you can do more and decompose a generalized vector and show that in the first case, this gives you some psi m and some lambda mn components, which are the gauge transformations of the tree form and the internal diffeos, or that's 11D, of course. So m is from 1 to 4. In a 2B case, you get again some psi n. You get some SL2 doublet. So I need an A index. You remember, M goes from 1 to 3. So I still need 4 and 5 to cover the full fundamental of SL5. The 4 and 5 is this little index A here. And then there is also, did I write this down correctly? Yes. Some singlet. You recognize diffeomorphisms, gauge transformations of the doublet of two forms in type 2B. And then something that doesn't have an interpretation, but luckily, if you plug it in the generalized derivative, this is trivial. It doesn't have an action on anything. So it's fine. And then indeed, you may check that these actually act in the right way on the fields. Okay. Questions? Okay, let me spend 2 minutes or 3 on the full theory, and then we'll move to generalized Schwarz. So what is exceptional field theory? It's a gauge theory of gen diffeos. Why do I say that? Well, remember we have this external spacetime with coordinates x mu, right? Our gauge parameters, our parameters for generalized diffeomorphism will generally depend also on the external coordinates, and they will depend on the internal ones up to section, of course. But that means that external derivatives don't commute with generalized diffeomorphism variations. You can think of these generalized diffeomorphisms as being an algebra that is being gauged because its parameters are local in the external spacetime. This will be perfectly familiar if L of lambda was just a Lie algebra variation instead of the complicated expression we saw. But the idea is the same. And so the solution is also the same. Recall that our maximum supergravities carry vector fields which happen to sit in the same representation as generalized vectors. So you may use them as parameters in the Lie derivative. And you may then covariantize your derivatives. Essentially exactly as you would if this curly L here just represented a Lie algebra variation in Yang-Mills theorem. No difference up to here. Then by requiring covariance, what does that mean? Suppose I have a field that transforms covariantly by definition. I want its covariant derivative to also be covariant. Just like in Yang-Mills. You will get the variation of the gauge connection. And that's going to be, there are different, people make slightly different choices. It will be the covariant derivative of the gauge parameter, but in fact, turns out that's plus trivial. So what is a trivial parameter? There might be some object, I'm gonna call it capital psi m mu, such that L psi, with psi as a parameter, is identically 0. You cannot catch an object like this by requiring covariance of the covariant derivative, because A mu only shows up inside the covariant derivative in the identity you need to prove. And so terms like this will never show up. They will automatically drop out of the expression. So the best you can do is you find the variation of A mu up to such trivial parameters. Then you may construct field strengths just like you would in Yang-Mills, but this time you want them to actually be covariant. You need to fix their gauge transformation. So when you get this, you find an expression for them. Actually, I don't think I'll want to. I think I'll cut this down a little bit. So let me put it this way. I need these objects to be actually covariant, the field strengths for A mu. Why? Because they will show up in the action. Imagine the kinetic term for the vector field is F squared, right? And so I want it to be covariant because it will contract this M here contracted with the generalized metric, which is covariant. So this is going to be, roughly speaking, let me write it as forms, something like this, you would expect just like in Yang-Mills, but then there will be some projector that depends on internal derivatives of some two forms. And all of this is going to be a trivial object. So something you cannot deduce from this identity. So basically there is a structure that starts showing up where to construct covariant field strengths, you have to worry about the fact that you only deduce the expression for the field strengths out of the identities like this up to trivial parameters. And then the gauge transformation of your field strengths are going to be covariant up to trivial parameters. You need to correct that. You want them to be exactly covariant. You add higher forms in the appropriate combination to compensate for that. And this keeps going at all levels up to the top forms and in your theory. And that's called a tensor hierarchy. It was first developed in gauge supergravity, not in exceptional field theory, but the structure is the same. That's all I'll tell you. It's just for you to understand that at the end of the day, what exceptional field theory will look like is maximal supergravity, covariantized under generalized diffeomorphisms, using the vector fields you have to build the gauge connection. And then a bunch of extra details on how you actually construct covariant objects. So let me stop here. I'll wait 1 minute for questions or for you to take a little bit of a break, and then we move to the last topic of the lectures. I'll take this minute actually to say something, perhaps. First, feel free to use the exercise session tomorrow also just to ask questions if you like. Use it however you want, I'll be there. And the other is, there are more details about the dynamics in the lecture notes, but I'd rather get to generalized Scherk Schwarz, so I'll drop that part, but you're encouraged to take a look.
Okay, thank you, Gianluca. So 5 minutes?
Yeah, let's make it, yeah, maybe 3. So I have 45 left.
Okay, great, thank you.
Good. Okay, so let me try to remind ourselves why we were doing all of this. So I'll focus on exceptional field theory in the way I speak, but everything I say applies to double field theory too. But especially in exceptional field theory, because of how I presented it, it's quite clear that the idea behind it is to rewrite certain supergravity theories in a way which is especially convenient if your space-time is of the form some external manifold of dimension d equal 11 minus n times some internal space. And internal space is going to be n dimensional for 11d or n minus 1 for type 2b. Okay, so why do we care about this? Well, in supergravity, we often want to look for solutions, right? Like, for instance, we may be interested in ADS cross some manifold solutions. And the manifold might be a bunch of spheres. And I'm sure you'll see some of such spaces in other lectures or in other places, also from the worksheet perspective. But these are, here the idea is also I want to find these solutions in supergravity, and it's not easy to classify all of them. Perhaps you're also interested in de Sitter or Minkowski as an internal space. Perhaps you want to exclude their existence, for instance. But even more generally, why not black holes, brains, domain walls, you name it. There are many solutions one can look for in supergravity with relevant physics. So what does exceptional field theory have anything to do with this? Well, obviously, let me perhaps mention the idea here is that you don't want to do a truncation. Well, at least we haven't yet done a truncation of the degrees of freedom along the internal space. But of course, the idea is that you choose the internal space to be the one where the y coordinates enter, okay? And the external one is the one associated with x. So it may be convenient to use exceptional field theory to look for these kinds of solutions. The reason is twofold. One has to do also, one is stressed more, that's the right thing to say. It's stressed more in the generalized geometry language, perhaps, but let me mention it anyway. The structure of generalized diffeomorphisms contains information about the geometry and the fluxes of the internal space. would be hard to show this directly within these lectures, but it's an important point. So somehow you geometrize the fluxes on the internal space by looking at generalized diffeomorphisms. We won't go there. There's something else one can think of though. In general, it might be convenient to consider a truncation of this form. Say all your fields are called phi, depending on x and y. I enumerate all of them and give them an index I. Okay, that's just running through all my fields. What if I could find a factorization answer like this? With another index and a bunch of coefficients, little phi lambda. Now, what if I could factorize the dependence on the internal space? Well, if you do it randomly, you have getting nothing. The important point is, what if the equations of motion of my original theory, 11D supergravity, think of these as being the left-hand side of the equations of motion, the right-hand side being 0, okay? Everything, and then you have to set this to 0. That's what I mean by equations of motion. What if these also factorize? There are as many equations of motion as fields, okay? So that's why I have the same index. What if they factorize and then you get some new, not yet known equations of motion for the coefficient fields only? Well, that would mean that if I solve these equations, as a consequence, I have solved the original equations. That's what we call a consistent truncation. Let me stress something. Consistent truncations don't necessarily define, and more often than not, they don't define effective field theories. So when you have a theory on a certain background, you might say, well, let's look at the spectrum of modes of oscillations around the background. Let's keep the lightest ones and drop the others, or integrate them out. Then you get an effective theory up to a certain energy scale, the one of the first massive mode you dropped. Consistent truncations don't do that. Consistent truncations pick a bunch of modes. Some might be light, some might be extremely massive, and drop others. They might be dropping light modes, might be dropping massive modes. It doesn't matter. All that matters is that if you solve the equations of motion in the truncated theory, you have a solution of the full theory. And where I'm focusing here is the case where the truncation is a lower dimensional supergravity theory. So, can you think of an example of a consistent truncation? Just from what's on the board. The trivial one is U equal to the identity. Then the capital I and the little lambda indices run over the same set of fields. That's the Kaluza-Klein reduction on a torus. Right? At the end of the day, that's what you do when you do Kaluza-Klein. All the rest are field redefinitions. But of course, that's not what we want to do. So one large class of consistent truncation is the one based on symmetries. Let me keep only the idea of consistent truncations. And let me call about consistent truncations based on symmetries. In particular, Scherk-Schwarz reductions, not generalized yet. So the idea here is you pick the internal space to be a Lie group, G. So G is parametrized by a some little g, which is an element of the group. And I'll just to remind you, this is the coordinates y now parameterize this element of the group, so they parameterize the G space. Well, but then, as you saw in other lectures too, you may consider the left or the right invariant one form, dmg, which one did I pick, just so that I can, yeah, I picked this one, fine. G inverse dmg. This is a bunch of one forms. I use E with a little circle here. And you can expand these in the generators of the Lie algebra associated to G. Okay? These are, what is it? Left invariant one forms on the group. They have a few nice properties. One is that they satisfy a Cartan-Maurer equation. And the other is that their inverses are vectors generating the infinitesimal action of G. So if I call Km, well, Km being EMN, the underlying index is the flat one. I think that should be clear. Then I have LKM, Kn is, depending on conventions, now I might be getting the sign wrong. I think in this case it's a minus, but might be getting confused. They close onto each other, these vectors. And the structure constants are, of course, the structure constants. These Fs here are the structure constants of the Lie group or the associated algebra. Okay? So now, Scherk-Schwarz reductions, the idea is you expand all fields in terms of these left invariant one forms. For instance, if you have a one form Cn of x and y, you say, well, now this is going to be some EMN and a coefficient which is only x dependent. Dot 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 for all your fields, the metric, etc., etc. Okay. One form on the internal space. So the idea you're still doing the splitting of legs into external and internal, and then you expand it this way, paying attention to GLD grading, blah, blah, blah. But the idea is this one. So what do you get at the end of the day? Suppose you do it for GR, just the metric. The Kaluza-Klein reduction of GR is giving you lower dimensional GR coupled to scalars and Maxwell vectors. The kinetic term for the Maxwell vectors is in fact non-minimal, it contains scalars, but that's what you get. What's going to happen here? Well, probably something similar up to a non-Abelian gauge structure, right? You're going to get GR plus scalars plus Young-Mills. What's going to be the gauge group of Young-Mills? Well, the one associated to the internal space. More precisely, the one associated to the left, to the right isometries of the internal space, the ones generated by K. Questions here? So why is this a consistent truncation? I haven't said that yet. Well, I did, but it's written so terribly that you can't possibly understand it. Now, equally terribly written, they are based on symmetries. So to convince yourself, I can't give you a full proof, that's too long. But to get an idea of why this is truncations based on symmetries, what is the symmetry here? It's the left action of the group on itself, no? Because you expand everything in terms of left invariant forms. So the coefficients here are invariant under the left action of the group on itself. The factorization matrices are invariant by construction, so everything is invariant. You're truncating your field space into a subsector, which is invariant under the left action of G on itself. So as a little exercise, let's do the consistent truncation, which is not dimensional. We don't change the dimensionality of the space. We just take two scalar fields. Flat space. And a potential, which is phi psi squared.
Gianluca, we have a question from the Zoom chat.
Oh, sorry, didn't show. Yeah.
No, I keep track of them. By Roger Aliyash, sorry if I mispronounce it. The question is, wouldn't the isometries of the internal manifold manifest themselves as gauge symmetries in the Kaluza-Klein reduction to what is new here? Yeah, okay, good. So when I said Kaluza-Klein reduction earlier, I meant Kaluza-Klein reduction on a torus. So the isometries are abelian, right? The isometries will be, you shift the angles of the torus by a constant. Those are your isometries. And those are gauge symmetries in a sense. They do reflect themselves in the lower dimensional theory. You have abelian gauge symmetries for the vector fields. They are Maxwell fields. The point is, none of the scalar fields or the fermions, if you look at SUSY, are going to be charged under those. Okay, because you're shifting coordinates, but there is nothing in the reduction ansatz that depends on the internal coordinates. So everything commutes with those transformations. In this case, instead, if you start playing with an internal isometry which maps the y coordinates, you know, to a different y, like the left action of the group would, well, your reduction matrices E, sorry, these are not invariant, but you'll see that, how should I put it? Let me put it this way. When you take the equations of motion of your theory, there's equations of motion contain internal derivatives dm in many places, right? So the reason the consistent truncation works is that all the internal derivatives that show up in the equations of motion, upon using such a factorization ansatz, will boil down to factors of the structure constants. Okay, all the internal derivatives end up inside structure constants, which are constant. And so they don't include any y dependence anymore. So that's the trick that makes it possible. And the difference with respect to the standard Kaluza-Klein reduction is that those structure constants are non-zero. So you have a non-Abelian structure. I hope that answers the question. But yeah, but thanks. That's an important point I should have stressed. The point is, when you think of the equations of motion of your theory, you take the derivatives, the internal derivatives don't just disappear magically. They are all absorbed into structure constants, which are constant objects. So it's fine to have them in a lower dimensional theory. We got a thank you. Okay, good, thanks. Okay, so the exercise is you pick this action and you ask yourself whether setting phi to 0 is consistent or setting psi to 0 is consistent. And then the second question is, what if now my potential is phi psi cube instead? I'll tell you why this has anything to do with Schwarz. The idea is that truncations are maybe based on symmetries. There is a Z2 symmetry here, which corresponds to flipping the sign of psi. And of course, that's lost when you change the power in the potential. The idea is singlets under a symmetry cannot couple linearly to non-singlets, otherwise the action would have been invariant. And that has an effect on how equations of motions are intertwined.
Okay, you cannot have a singlet source by itself, a non-singlet. You need to source some higher power, and then that affects how the equations of motion look like. You're encouraged to do that, and we have time tomorrow to discuss it. That's not a full proof, but it should give you an idea of why using symmetries to glue consistent truncations works. Okay. Now I want to go back to exceptional field theory and to generalized Schwarz. Okay. What matters here is essentially this equation. In this case, what made the consistent truncation, or the structure of the consistent truncation, was encoded in a bunch of vectors in the internal space. These vectors have the property that they close onto themselves with constant coefficients, and those coefficients are structure constants of the algebra. So generalized Schwarz. Let me check I'm not forgetting anything I really need to, I was really planning to say before I get here. I think the order is correct. Good. So let me play a similar game by using something we mentioned in double field theory last Monday. Suppose I have a matrix, UMN, which belongs this time to exceptional group. But again, let me stress, you could play the same game in double field theory and just stick into exceptional because I already have this factorization structure written down, okay, naturally. Now, this is a collection of generalized vectors, right? The m dot index is a spectator. We mentioned last week that I can, Monday, that feels like a week, that I can compute generalized derivatives of these objects acting on each other. And because these matrices are invertible, whatever I write on the right-hand side, I can always write in this form in terms of something called a generalized torsion. There's nothing new here. I've done nothing. This is literally always true. As an exercise, you can find the expression of T in terms of the Y tensor. Remembering that the Y tensor is invariant under En cross R plus. Now, you see how this looks a little bit like having vectors, a square matrix of vectors KMN, and saying, well, if I have the Lie derivatives of these vectors on a space closes onto a Lie algebra, then I have a Scherk-Schwarz consistent truncation. You hopefully see that there is something similar. The thing is, this has to be a Lie algebra. These Fs here need to be constants and satisfy a Jacobi identity. So that's what I'm gonna do. I'm gonna say this, so from now on, I call it X. I just changed the name to remind myself that I want it to be a constant. And then as an exercise, which you already were asked to do in the double field theory part, show the Leibniz identity for L implies a certain quadratic constraint for X. Okay, this is an exercise in the double field theory part at the very end. And it's the same computation in this case, so it doesn't matter if you do it in double or exceptional field theory. Okay, that being said, the statement is, if you find such matrices, that's going to restrict what the internal space is. In this case, it tells you that the internal space was a group manifold. Here, it's going to be something a bit more general. And that's what we call generalized Scherk-Schwarz. Proving that using these matrices to write down a factorization answer that gives you a consistent truncation is non-trivial. But yeah, eventually it works. Let me say how you do factorize your fields. Well, the advantage is in exceptional field theory, all our fields sit in representation of En cross R plus. So we will just write down naturally the factorization ansatz, right? So our vector fields A mu m of x and y are going to be some coefficients A mu m dot of x, U m dot of y. Similarly, your matrix M, let me write it without indices to be a little bit faster because I'm a bit late. It will look like U transpose of y, some coefficient M of x, U of y, and so on. Okay, just following the representation. And actually, this thing is unimodular, so there is going to be a factor of the determinant of U, which should be 1 over, well, I don't remember right now. I wrote it down somewhere, but I lost it. Remember, U is not unimodular. It has a weight, so you need to make sure you keep that into account. But yeah, these things are automatic if you pay attention to the representation theory and the R plus charges. The statement is this gives you a consistent truncation. So I need to tell you two things now. What's the final theory, right? Well, the final theory is going to be d-dimensional for sure, because the only coordinates left are the x. And it's going to have a gauge structure. Remember, in the standard Scherk Schwarz, the gauge structure was the structure constants from these vectors. This time, the gauge structure is entirely specified by the generalized torsion, this x here. So we get to d-dimensional gauged maximum. Maximal because I'm doing ExFT, otherwise some subsector for double field theory, gauged maximal supergravity, where the gauging is entirely specified by this x, the constant generalized torsion. Now you say, am I going to spend how much time introducing gauge supergravity to you? Well, as little as possible. I'm going to do something I feel a bit bad about, but sorry, that's way too slow, way too quick. Let me just scroll away a little bit of stuff and put this x upwards. The gauging is specified by generalized torsion. So what is gauge supergravity? So this is the same, roughly speaking, as ExFT. So you would write it in a similar way, following the structure of the tensor hierarchy and the covariantization of the action of ungauged maximal supergravity. But this time, your gauge algebra is not defined by some Lie derivative L lambda. Let me remind you, this had a transport term and then some projection onto your Lie algebra of your exceptional algebra of d lambda, right? That's roughly speaking the structure of generalized Lie derivative. This time this becomes just some, let me use dotted indices, and this lambda is going to be small to remind myself it's now only external. Some gauge parameter, some matrix. Sorry, this then needs to act on a field, right? And then the ENN variation of your field. No? The idea is you pick the rigid transformation of your fields under En. You select a subset of them by using some matrix theta, and you couple them to external parameters. That's how you will gauge a subset of your En symmetries, of your global En symmetries, in just, say, d dimensions. This is called the embedding tensor. And it sits in a representation which is called R theta and shows up in the tables. Actually, it's R theta plus R1, usually. You find it in the lecture notes. I won't get into that. But so the crucial point is that by construction, it turns out that your generalized torsion that you get from generalized diffeomorphisms is always decomposed in this way. Well, let me put perhaps a hat to remind me that the R plus generator is also there. So writing X or writing theta is exactly the same thing. The generalized torsion defines exactly your gauge supergravity. You can think of the generalized torsion as picking a subalgebra of En and telling you, well, now this subalgebra is going to be gauged. It's going to be a local symmetry. The vector fields in your theory, the ones after reduction, will play the role of gauge connection, just as I reviewed very quickly for exceptional field theory. And in a sense, it's gauge supergravity, it's more familiar. You're really just gauging a Lie algebra now. And the structure of field strengths, covariance, and so on follows a similar story. Questions here? Okay. This is not making gauge supergravity justice, but it will have to do for today. There is, however, one thing I really need to mention. I got here from exceptional field theory mentioning this generalized Schwarz. There are a few comments I really need to make. One, there exist gaugings, let me call the gaugings theta. So there exists maximal gauge supergravity such that there is no generalized Schwarz that generates them. So not for every consistent theta or X, there is a matrix U that gives it that. In some cases, you cannot find it. There may be a gauge supergravity with a certain choice of X that looks like something you could get from generalized Schwarz as a generalized torsion of a generalized Schwarz, but that's not the case. You can prove that it's never going to work. Or, so that doesn't exist. Or perhaps it's unique. So let me put it here. Perhaps it's unique. There is only one way, one generalized Schwarz reduction of 11D sugra or 2B sugra that gives you that gauge supergravity. Or perhaps there are many. All these situations can arise. So perhaps a little drawing can help now. Let's say I start with a gauge supergravity now. Let's do a bottom-up situation. I find a gauge supergravity with gauging defined by an X or theta. X and theta are the same. Okay? And perhaps, okay, and let's say that I do know that this specific gauge supergravity comes from a generalized Schwarz with a matrix U from XFT. So really from 11D or 2B supergravity. Then the nice property of gauge supergravity is that they have plenty of solutions. They have a potential for the scalar fields. You may find extreme of this potential corresponding to DS or anti-de Sitter or Minkowski-Vakia. You can, of course, find solutions that are not maximally symmetric, so black holes, brains, and so on. So you find some solution. So you solve the equation of motion in the truncation theories. That's the thing you didn't want to do in full 11 dimensions because it was too difficult. Sometimes it's easier in the case of supergravity. So you find a solution, but then plugging back, dressing your solution with your U matrix, you uplift. To a solution in higher dimensions. This is not theory, this is done a lot of times. And that is how you solve the equations of motion of your original theory. But what happens if you have more than one uplift? Perhaps there is another generalized Schwarz. Then your solution can be uplifted, although the arrow goes down now. So here you're uplifting with U, here you uplift with U tilde, and you find a solution, which is a different one. So this is the framework, the general one I was talking about at the beginning of the lecture, where in some cases, non-Abelian dualities can be interpreted from the point of view of such different choices of generalized Schwarz ansatz. Okay, so there are cases where you may then say these in different solutions, they are dual.
Gianluca, just to say you have 10 minutes.
Yes. Other questions? Okay. So let me stress the one place where there is a technical assumption is that you may consider when you do non-Abelian duality, you don't necessarily have to start with something that belongs to a gauge supergravity truncation. Or perhaps it belongs to one, but not one down to maximal supergravity. There exist other truncations that truncate you to theories with less supersymmetry, and I'm not even touching on those. Or perhaps the generalized torsion is just non-constant, not even a single element of it. Okay, so in general, that's not guaranteed that all non-Abelian dualities will always be interpretable in this framework, as far as I know at least. But when it's possible, it's a nice target space interpretation of what's going on. In particular, if you remember your matrix M of the solution, of the above solution, of the solution on top, is going to be given by sandwiching the gauge supergravity solution straight M with the twist matrix U. The other solution, let's pretend we only look at M and not all the other fields, A, mu, and blah, blah, blah. You understand that the same will work for them. Is given, there's going to be another solution obtained, uplifted by using a different twist matrix, but the very same straight M. That's always the gauge supergravity solution. And then if you manage to align sections, make sure that the y coordinates are embedded in your one representation in the same way, then these two are clearly related by U tilde U inverse. So you have a y-dependent, a coordinate-dependent element of En that maps one solution of 11D supergravity states to another. In fact, you don't have to solve the equation of motion. It might be just a background that is not a solution. And that would still work. Target space, of course. Worksheet is a different story, but here you could do it for any configuration. Okay, so in the last few minutes, I'll first encourage you again to ask questions. If you need time to think of questions, let me remind you there is Slack. There is an exercise session tomorrow afternoon. And don't use it only for exercises, use it for anything you want. And of course, I understand you have plenty of stuff also from the other lectures. That's obvious. So the last thing I want to try to say is what are these spaces, okay? So I'll need a blank slate for that. So let me remind you of something. What happens if I contract a generalized vector with a derivative, which is on section? Well, necessarily, you can guess this from the transport term of the generalized derivative. This gives you the vector component, the one generating infinitesimal coordinate transformations inside of lambda. So there is a nice structure here where suppose I now do this, L lambda of V, M, but now after computing this, I restrict to the vector component inside V. Well, it turns out that the only element of lambda that contributes to this expression is psi itself. So this reduces to the standard Lie derivative between these two vectors, psi belonging to lambda and k belonging to V. If I now do this, I can play this game, of course, also for my twist matrices, right? Why not? I compute this and then restrict only to the vector components. I know which ones they are because these matrices need to be on section. This is, I call these components Kn, Kn, and these close into an algebra. Just using the definition of generalized torsion. So these, they realize your gauge algebra specified by X. Remember the relation with this theta that defines your gauge algebra. They realize it on the internal manifold. I have a bunch of vectors in my internal manifold that generate infinitesimal translations, and they close into a Lie algebra. So they realize this Lie algebra on the internal manifold. Okay, nice. But then the fact that U is invertible tells me that this matrix here, Km M, has maximal rank. Otherwise, U wouldn't be invertible. If it has maximal rank, that means at each point on my internal manifold, I have the internal manifold at dimension n. I have n independent vectors out of these. So I can use them to move around on a little patch, stretch around a little bit and construct a little bit of my manifold, just using this case to translate a little bit. At some point, I'll have to stop because one of the vectors I used may vanish, but it's guaranteed by the fact that I'm assuming that this equation is satisfied globally, that at that point, I'll find another set out of these vectors that allows me to play exactly the same game again and generate another little patch of my space. And then I'll keep doing this everywhere until I construct the whole space just out of a Lie algebra action, the exponential of it. So what this tells me is that I admits a transitive action of the gauge group, some global form of the gauge group. I'm ignoring the center for the quickness sake. So if it admits a transitive action of my gauge group, my internal space needs to be, in the most general case, a coset space. How do I identify the denominator? Well, it's the algebra given by the vectors, the subset of these vectors that leaves my starting point invariant. That's the isotropy group or the isotropy algebra. Sorry, my son. Sorry about this. Of horseman Hamlet. Okay. Well, perhaps that helped with the emphasis. Starting from this, one could do something that I'm afraid it's going to be hard to do in 1 minute. But perhaps I'll take 2 minutes and the organizers won't kill me for trying. Okay, very good. But now, can I say something more about these manifolds? First of all, it's not true that every coset space gives you a generalized Schwarz. That's absolutely false. But I can try to learn something more. So say that in this space here, I have a coset representative such that under the transitive action of G, I call it L, this coset representative. I'm using my lecture notes, the appendix has some notes on this. I'm going to say that the action of G gauge maps it from the point Y to the point Y prime is given by this acting on the left. I hope I made the right choice. Let me check just so that I don't get wrong signs at some point. Of course, it's the other one. So I choose the right action rather than the left. So it turns out that there is a construction of the vectors here, just out of the knowledge that my space is this coset space. Let me use A for the adjoint of G. Okay? The adjoint is smaller than M dot in general. And I swear I'll be finished in just a couple of minutes. So let me remind you something. You can construct on a coset space Cartan-Maurer one form, and you expand it into coset generators. So those elements of the G gauge algebra that are not in H, you just pick a basis, whatever you like, as long as they're linearly independent, plus then blah, blah, blah stuff in H, which I won't write. That's an H connection. Okay, so this underlined M index turns out to be, in a sense, the flat index along the internal space, and it's a subset of the index A I'm writing here, which is the full adjoint. So you can construct vectors generating a transitive action of G just by doing the following. You take the inverse of L in the adjoint representation. Okay, here I didn't specify the representation. Let's say it was a faithful one, whatever you like. Now I really write it down in the adjoint representation. I project this index onto the coset generators. No, it's just a subset of the range of A. And then I make it curved with the inverse of the coset components of the Cartan-Maurer. That's just how you construct the vectors. This has nothing to do with gauge supergravity or exceptional filter. Just standard constructions on the coset. But then let me remind you, what you should ask, well, what is Km dot M or Y? Well, we said we had a matrix that mapped gauge elements into R1. We called it theta. You might complain that this index used to be an alpha running on the adjoint of the full exceptional algebra. But of course, this matrix is only non-zero along the adjoint of the subalgebra, which you gauge. And that adjoint is exactly A. So I get here. Good. We're almost done. Now let me point out something. I ask you to compute a quadratic constraint for a generalized torsion. That constraint tells you that this matrix is gauge invariant. You can rephrase it in these terms. And also, the gauge group is embedded inside the exceptional group. So that means that I can move this matrix L in the adjoint representation and bring it to the R1 representation through theta. Now, the adjoint index on the embedding tensor gets projected onto the coset in the process, and then you dress it. So why is this? Why am I doing this at all? Well, because now, last piece of information is the following. Remember the section constraint. And remember that Y is invariant under En. So that also means that if I just pick the same tensor with dotted indices, this has to be true. Because this is U M dot P dP. And U is an exceptional element, so it leaves Y invariant. It goes through, passes through Y. L minus 1 is also an exceptional element. So we arrive at a necessary condition. It tells you that the coset projection of your generalized torsion needs itself to satisfy the section constraint. If you want the generalized torsion to actually be a generalized torsion, to actually admit some internal space and some matrix U that generates it. So why did I want to get here and stop here? That's because these kind of requirements show up in a few places with different names. In double field theory, remember a section constraint is the choice of a maximally isotropic sub-vector space of the vector representation. There is a notion of Drinfeld double that shows up in Poisson-Litty duality, where indeed you have some algebra, think of the algebra defined by the generalized torsion, which admits subalgebras that are maximally isotropic. And then that gives you generalized Schwarz twist matrices U, given by the fact that you quotient out your large group, that your full group, by the maximal isotropic algebra. And if you have two of them, you can choose which one to quotient out. And that gives you different generalized Schwarz, and so a non-Abelian duality. In exceptional field theory, other languages like exceptional Drinfeld algebras, Poisson-Lie U duality or U plurality somehow always end up playing, having to do with requirements like this because they have to do with generalized Schwarz. This is a necessary requirement. In some cases, it's sufficient. Let me remind you, you have a coset space and you have to do a projection onto coset generators. Yeah. It's sufficient for double field theory. And recently it was showed that it's sufficient for 11 histogram, not type 2 beta. The way it happens is that all the information you have on the board has to do with the K components of this U matrix. You know nothing about the rest of it. So does the rest follow automatically or not? Well, the answer is in some cases, yes. In some others, no, there's some more to ask. I'll try to get to the exercise session, writing something down in Slack channel with a couple examples of how this connects to other stories in the literature. And that being said, I'll stop and thank you for your attention.
Okay, thank you, Gianluca. Let's give him a round of applause.
I'll also add some references.